Welcome to the Emergence Podcast, where we discuss interdisciplinary and collaborative work that connects to U of I physics. A quick disclaimer before we get started: the views expressed in this podcast do not necessarily represent those held by the physics department or the University of Illinois. I'm Maddie Stover, and today we are joined by Sir Tony Leggett. Sir Anthony J. Leggett, the John D. and Catherine T. MacArthur Professor and Center for Advanced Study Professor of Physics, has been a faculty member at Illinois since 1983. He is widely recognized as a world leader in the theory of low-temperature physics, and his pioneering work on superfluidity was recognized by the 2003 Nobel Prize in Physics. He is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, the Russian Academy of Sciences, and is a Fellow of the Royal Society, the American Physical Society, and the American Institute of Physics. He is an honorary Fellow of the Institute of Physics of the UK, and he was knighted by Queen Elizabeth II in 2004 for, quote, services to physics, unquote. Welcome, Tony. Thank you for joining us.
Pleasure to be here.
Starting with some questions about your work at quantum at the macroscopic scale. Historically, the effects of quantum mechanics are only seen at very small scales. For example, on the scale of single electrons. Much of your work has been on quantum effects at the macroscopic scale, such as superconductivity and superfluidity. Can you tell us about some of those effects you've studied?
Right. Well, I think one has to distinguish two different kinds of effect when one was talking about superfluidity or superconductivity. In the first place, you can have a large set of microscopic particles, electrons or atoms or whatever, which each individually behave according to quantum mechanics. And under certain circumstances, they may all behave in pretty much the same way. And so in this way you amplify a microscopic quantum effect to a macroscopic or everyday level. This has been quite well known, has a long history. It's not what I'm primarily interested in. What I'm more interested in is a situation in which quantum mechanics, if taken literally, tells us that some kind of reasonably macroscopic or everyday level object is itself behaving in a quantum mechanical way. In other words, it may not be in a definite macroscopic state. An example of this, which I've studied in some detail, is a so-called flux qubit. That is a superconducting ring which is interrupted by a single junction of a kind we call Josephson junctions. Now, the behavior of this beast is in some sense governed by the first kind of quantum mechanical effect. But what is interesting is that because of this behavior, you may get a situation in which if you take quantum mechanics seriously, then you have you could have a current flowing, say, clockwise with a certain magnitude, or the same current flowing anti-clockwise with the same amplitude. But in fact, quantum mechanics says that under certain circumstances, that's not what happens. You may get a so-called quantum superposition of these two possibilities. In other words, this reasonably macroscopic object is not in a definite state, but in a quantum superposition of two macroscopically distinct states. And that's what I've been primarily interested in myself.
Okay, fantastic. That actually leads quite well into the next question. So room temperature superconductors are highly sought after due to applications such as transporting energy from its source to a home with almost no energy loss. You devised an experiment for testing the symmetries of a certain class of high-temperature superconductors with your late colleague, University of Illinois Professor Van Harlingen. What were the results of this experiment, and what influence did these results have on the field of high-temperature superconductivity?
Okay. Well, let me just give a little background. Generally, superconductivity is believed to occur because electrons get together in pairs, and then these pairs, rather than the individual electrons, all behave in the same way. And so when the so-called high-temperature superconductors were discovered in 1986, this was the general assumption about how things worked. But that raises an important question. The electrons are coming together to form pairs, and in some sense you can think of these pairs as like giant dielectronic molecules. The difference from ordinary molecules is that in ordinary molecules, for example with water or whatever, the size of the molecule is usually at least as small or smaller than the distance between different molecules. That's not the case in superconductivity. Rather, the size of the pairs is large compared to the distance between them. So, in some sense, so people sometimes compare this to a form of modern dance, in which my motion might be correlated with that of my partner, but she's way across the room. And between us, there are any number of other pairs doing their own thing or doing similar things. And that's roughly speaking what is believed to happen in superconductivity. Well, that raises an important question. What is the internal state of the pair? In the old-fashioned superconductors, it's generally believed that the internal state of the pairs is actually rather boring. It's said to be isotropic, which means it looks the same whichever angle you look from, and it's also spin singlet, meaning that the spins of the two electrons involved get paired off in an opposite way. It wasn't obvious at all that was going to be the case with the high-temperature cuprate superconductors. And in fact, in the early days, for the first few years, there were really two major schools of thought. One of them held that, well, it isn't really all that strange. These giant molecules, so-called Cooper pairs, they're pretty much like what happens in ordinary superconductors. That was called the so-called S-wave hypothesis. In that case, they wouldn't have any particularly exciting features associated with their internal structure. The other alternative which people considered was a bit more exciting. It held that perhaps the internal structure of the pairs was not so trivial as in the ordinary S-wave case. And there was a particular hypothesis called the D-wave state, which held that indeed these pairs were anisotropic. They looked different when viewed from different angles. If you looked at it from certain directions, in fact, the pair, or the order parameter, the pair wave function, was zero, which produced some interesting consequences, or would if it were true. So there were these two hypotheses out there, and they were both of them were embraced by people who had a considerable reputation in the general field of superconductivity, and arguments flew backwards and forwards. So I sat down and asked myself, can I think of some experiment which might be able to resolve this question? And I finally came to the conclusion that there was also a kind of experiment you could do which involved circuits, electronic circuits, which contained so-called Josephson junctions, a peculiar type of junction between two bulk metals. And those circuits would behave differently depending on whether you had an S-wave or a D-wave order parameter. And so I it turned out, incidentally, at the end of the day, that this is not a really very original idea. There was a Russian group which had actually proposed this in a different context than the cuprates some years previously, but I didn't know, or at least I didn't sort of consciously know about this, so I thought it was quite an exciting idea. So I proposed this to my colleague Dale van Harlingen, and he got his team together and did the experiment. And at least in our opinion, it came out rather firmly in favour of the D-wave hypothesis, which meant that there were all sorts of exciting things associated with the relative wave function, relative order parameter, which you could do with these cuprate materials that you really couldn't do with the conventional superconductors. So that was what I think what made the discovery exciting. It was not entirely uncontroversial from the word go. There was some opposition to it from people who still believed the S-wave hypothesis. And there were some experiments which seemed to possibly come out against it. But I think one can say that it was cleared up to most people's satisfaction within a year or two. And so I believe that nowadays the overwhelming majority of people working in the area do believe that the order parameter is D-wave, that is the exciting kind.
Great. And could you just repeat again, what is it about the support for the D-wave hypothesis that was particularly exciting for high-temperature superconductors?
Well, in a way, it's sort of not so exciting, but rather a bit disappointing, in the sense that if I have a D-wave superconductor, it means that it's very easy to excite it by finite temperatures. And that means that the superconducting properties get, as it were, degraded with finite temperatures, and they get degraded much faster for a D-wave superconductor than
and
for the
by
S-wave.
finite temperature, do you mean, what do you mean by that?
Well, simply that, I mean, theorists, of course, experimentalists, when they have a sample, that sample is always at some kind of finite temperature. It's in contact with its environment, and that environment is going to exchange heat with it, and as a result, the superconductor itself is at finite temperature. And although you can get it down to a remarkable degree, you can't get it down to zero temperature. So finite temperature just means not zero temperature. I mean, zero temperature is a theorist's abstraction. All real experiments are done at finite temperature. But what it the relevance of that is that if you ask how quickly do the superconducting properties get degraded when I heat the material, the answer is they get degraded quite a bit faster for a D-wave than for an S-wave superconductor. Okay. So that really is, in some sense, a bit disappointing, but it seems to be the case.
Okay, disappointing, but very useful for needing to construct these.
Yes.
Okay, fantastic. Thank you. On the topic of high-temperature superconductors, in your opinion, why don't we have them already, and are you optimistic that we'll have them in the future?
Well, actually, we do have them already in some sense.
The high pressure.
Exactly. If I can not only heat my sample to room temperature, but also compress it to an enormously high pressure, as I can in, for example, an anvil diamond cell, then I may find that it's superconducting. And in fact, that's been a major surprise over the last few years. It was originally thought that that really even the so-called high-temperature superconductors could not be superconducting at room temperature. But in fact, this new class, there's now a separate class, nothing directly to do with the cuprates, which does look as if they are superconducting at room temperature, or at least very close to room temperature, but at these enormous pressures. So it's not really of great practical use as such. However, what people have started to do in the last year or two is they've tried to do an experiment in which you apply a huge pressure and so induce the system to go superconducting at room temperature. And then what you try to do is to gradually take the pressure off while maintaining the temperature still room temperature and see if you can keep the superconductivity.
Oh, okay.
And there's been a certain amount of success along those lines, although it's not enough to make it practical right now.
Okay. So what is the kind of the reasoning behind why we don't have room temperature superconductors at, kind of reasonable pressures?
Well, we don't really know, but the general belief is that since the forces which tend to form these so-called Cooper pairs, these giant molecules, since these forces are rather weak, they will be disrupted by thermal, that is temperature-dependent effects rather easily. That's not entirely obvious. We may yet find that there are materials which do show superconductivity at room temperature and room pressure. That would be very exciting if it happens. It hasn't happened so far, but we can still look.
And are you optimistic that we would find those materials in the future?
Yeah, somewhat, I think. Of course, your next question could be, okay, where should we look for them? And of course, the answer is I don't know. Otherwise, that's what I'd be doing.
Good. Questions for the future. So transitioning a little bit to your research in the fundamentals of quantum physics.
Yeah.
You graduated from Oxford with a degree in classics. Has your philosophical training impacted your approach to physics?
Yes, I think it has. Philosophers, almost as a matter of definition of their profession, tend to ask all the time, asking two questions. One question is, what do you mean? And the second is, how do you know? And these are not questions which physicists are quite so used to asking, particularly the first. And so I think my philosophical training has made me very conscious of the fact, first of all, that you should not just assume that a question you pose or a statement that you make has an ambiguous meaning. You do have to watch that quite carefully. And secondly, you ought to be always conscious that when you have a particular belief, let us say about the physical world, that has in the end to be based on some kind of experiment. In other words, how do I know this is right? Again, obviously physicists do this, but I think they're less conscious all the time that they have to be aware of this, as I think I am.
Great. So in quantum mechanics, just a little background for our listeners, a quantum particle can be in more than one state at once, as you alluded to before. For example, in both the spin up and spin down state. One way to think of this is in a thought experiment called Schrodinger's cat. In this thought experiment, there is a radioactive device that is a, say, 50% chance probability of decaying and a 50% probability of not decaying. In a box with this device is a cat, and if the device decays, the cat will die, and if it doesn't decay, the cat will live. In this scenario, the cat is in a superposition, being in more than one state at one time, until you open the box. The current common understanding is that when you open the box, the cat superposition collapses into either dead or alive. However, some believe quantum mechanics may be incomplete because of an issue with experiments like this known as the quantum measurement problem. Can you explain the quantum measurement problem?
Well, it is precisely the question of how you get from a description which you believe to be correct at the microscopic level, in which at least microscopic objects and perhaps also macroscopic ones can, under certain circumstances, can be, if you like, simultaneously in two different macroscopic states at once. You have to be able to go from that description to a description in which the cat is definitely in one state or the other. Presumably, of course, the animal protection societies have prevented us from doing this experiment in a statistically meaningful way, but presumably if you were actually to do this experiment with a real-life cat and open the box, you would find her, in each case, either to be dead or to be alive. And we believe that the probability, at least in simple cases, would be half and half. So the question is, I think John Bell, English physicist who died some few decades ago, he had a nice way of putting things, and the way he put the dilemma was, how do you go from an and to an or? Okay, in the quantum mechanical description, the cat is in some sense both dead and alive. In the common sense, everyday level description, she's either dead. Each particular cat is either dead or alive. So how do you go from one description to the other? And the answer is we really don't know. It's embarrassing, but we don't. There have been various specific proposals for detailed theories which might take you from one description to the other. There are a number of such theories in the literature. One which is rather well known is due to Girardi, Rimini, Weber and Pearl. They postulate a sort of universal noise background whose function, or part of whose function, is to convert the and into an or. People have tried to test this or put limits on the parameters which occur in this theory, and they've made some advance, but I certainly don't think you could say they've either confirmed or refuted this proposition right now.
Is there a particular theory that you're kind of most drawn to in terms of going from the and to the or?
No. I believe that there must be some way, and that by itself is a somewhat revolutionary hypothesis, because it means that in order for there to be some way, it must be the case that quantum mechanics is not the whole truth about the physical world, which is sort of contrary to the belief of most practicing physicists. Most practicing physicists, I think, would like to believe that in some way or other quantum mechanics is the whole truth, but then I find it difficult to avoid the Schrödinger's cat paradox. And so I believe that can't be right, and that makes me a minority in the field.
What experiments that you know of are being developed to probe the quantum measurement problem, or kind of test
the ones I know most about? I worked on these before they actually existed, as it were, theoretically, and I've tried to analyse them since they've been done. They're on so-called flux qubits. These are superconducting rings threaded by a single Josephson junction, and as I mentioned previously, in such a system, quantum mechanics says you can get a superposition of current one way or current the other way. And so I've been interested in trying to devise experiments which will either confirm or disconfirm this hypothesis. And an experiment was done at NTT in Japan a few years ago. I'm a co-author of the paper, though my role was somewhat minimal in this experiment. And basically, they found that given a couple of plausible assumptions about the system, then quantum mechanics is right at that level. In other words, the system is indeed in a quantum superposition of these two different states.
At the macroscopic level?
At the macroscopic level, yeah. And then the interesting thing is you can do a very small tweak on that experiment, as it were, just fire in what looks like a very, very tiny pulse of current. And that then converts you from the and into an or. Experimentally. So that just leaves the problem there. I mean, it doesn't solve the problem. It leaves it there, but it does say that quantum mechanics is working at that level.
You kind of were quoted in a article about this, about some of the philosophical implications of this 2016 experiment. Could you kind of give a summary of what potential philosophical implications could be?
Okay, well, there was in a completely different field of human behaviour, there's a famous quotation when a particular politician was asked a certain question. He replied, this is historical, he replied, "It depends what the meaning of is." And that is very much the case in physics. The outcome of these experiments does make you question what you mean by saying, or what you would mean by saying, that the system is in a definite macroscopic state, rather than being in some kind of superposition, say. And so that in turn gets you onto the question of counterfactuals. I mean, a sort of typical counterfactual statement would be something like, had I got up 10 minutes earlier this morning, I would have caught the 8 o'clock bus. I mean, the premise there is counterfactual. I did not get up 10 minutes earlier. And so, I mean, long before quantum mechanics, philosophers have argued about the meaning of this kind of statement. And there are one or two rather famous philosophy texts on this. I don't think they really help very much in the physics problem. They just put it in slightly different words, as it were, which is sort of in some ways rather typical of the interaction between philosophy and physics, I think. But I mean, if one ever does get a resolution, an agreed resolution to the quantum measurement paradox, then one may have contributed something to philosophy, I think.
Oh, very interesting. So on this kind of topic of macroscopic quantum systems, could you give us some examples, if any, of kind of practical implications of macroscopic quantum realizations that we could have in everyday life? And kind of what are the key questions that we need to answer to gauge the importance of these systems in everyday life?
Well, at least until recently, I don't think one could say that there have been many everyday life applications. That's changing because of the development of the field known as quantum computing, which does depend on the ability to put macroscopic systems, in this case flux qubits, in some kind of superposition state. So quantum mechanics will only go on working so long as the superposition principle continues to hold. So from that point of view, right now you might say that's very much an academic subject, but I think it's pretty likely that quantum computing is going to become almost a routine tool within the next generation or so.
A bit about kind of your life outside of research. So outside of research, rock climbing was a big interest of yours.
Yeah.
What climbing route are you most proud of completing?
Well, to be honest, I think the most distinguished or noteworthy climb that I've done was not in fact really rock climbing, or mostly not rock climbing. It was mostly just slogging up snow. And that was the Allinhorn in the Bernese Oberland of Switzerland. I think it's the Bernese Oberland. Anyway, the Allinhorn is a quite well-known peak. It actually has a Wikipedia entry. I looked it up, and it was I think a memorable experience to do that climb.
What is the elevation of that?
About 4,000 meters, somewhat over. It's people tend, for one reason or another, to attach a special significance to peaks which are over 4,000 meters. So,
understandably so.
The other achievement which I sort of pick out is again not at all distinguished. It's a rather easy, on the scale of rock climbing, at least as developed in the UK, is a pretty easy climb. But it was the reason I call attention to it is that the poet and author Robert Graves actually wrote an autobiography, I think, called Goodbye to All That. And one of the episodes that he mentions in that book is that his first exposure, or his first lead for a rock climb, was this climb on a particular face in North Wales, I guess, called Gambit. And that was, again, precisely the first lead that I did. So I felt that was somewhat noteworthy.
Yeah, it kind of captured you both in the same way to continue the sport. Awesome. So you also, earlier in your career, taught in Ghana for 2 semesters.
Yes.
What did you take away from that experience?
I didn't know what to expect when I went to Ghana the first year. And one thing that was unexpected was how much spare time I had. Once I'd done my teaching and any preparation I needed to do for the next set of lectures, basically there was nothing much that I had to do associated with my job. And so I had a certain amount of spare time. I thought, why not try to do a bit of research? Well, easier said than done, because it turned out that UST did have a library, and it did subscribe to many of the leading international journals, like Physical Review and so forth. However, the librarian should have been retired many years previously, and he was really very superannuated and not terribly competent at his job, and so these journals were not shelved in any sensible way. They could just land up anywhere in the library, which is a large place. And so I after a few days, I concluded that there really wasn't much point in trying to look for the journal literature on any given subject. So the sensible thing was to try to find a research topic on which there was no existing literature. And so I came up with non-local hidden variable theories, and did a bit of work on that. And at the time I sort of wrote it up, but it didn't seem terribly important. So I just let it sit in a drawer. About a quarter of a century later, I was invited to a retirement ceremony for David Mermin at Cornell, and he's someone who very much shares my interest in the foundations of quantum mechanics, and we corresponded a lot on that subject. And so I thought, what can I reasonably contribute to a Festschrift for? I was asked to contribute a paper to the Festschrift for his retirement, and it occurred to me that maybe I should contribute this work that I'd done in Ghana. It was by that time it's a quarter of a century old, but I thought, well, worth a shot. Well, of course, as usually, it turned out that by the time it was published, it was really obsolete because people had gone that far and beyond it and so forth. But still had, I mean, it did actually trigger an experiment which might not otherwise have been done. So,
Okay, what was the experiment?
well, it was on photons. It was done at the IQOQI, that's the Institute for Quantum Optics and Quantum Information in Vienna. There's a big group there which specialises in that kind of thing. And so they actually were able to rule out a particular class of non-local hidden variable theories.
Okay.
But as I say, by that time my result had been published in more sophisticated terms in the literature.
Mm. And just for our listeners, non-local hidden variable theory, is that one of the theories that takes you from the and to the or?
Not really. I mean, it has more of a function at the level where you believe that quantum mechanics is still fully operative.
Oh, okay. Okay, gotcha. In 2004, you were knighted by Queen Elizabeth II for, quote, services to physics, unquote. Do you have a favorite memory from that day?
Oh, yeah. Well, I was lucky. In the sense that I was in fact knighted by the Queen herself. That doesn't happen by any means to everyone who gets a knighthood, because there are lots of these ceremonies, just about one a week I think throughout the year, and for most of them the Queen herself doesn't go. It's a minor member of the royal family who goes and actually confers the knighthood. But in my case, I was lucky. I did get the Queen herself. And so, no, what I actually remember was that they pin a sort of little what do you call it, a hook on your suit, which is to allow the Queen to put the appropriate medal on you. Mm-hmm. So she has to put the medal on the pin. Mm-hmm. And so she was fiddling around with this, and the first words she spoke to me said, "I always have trouble with these things, you know."
Oh, that's very human. Yes, very humanizing.
Yeah, well, I was quite impressed actually, because I mean, by the time she did this for me, the Queen was in her 80s, I think, or certainly her late 70s, and she had to stand there on the stage for something like an hour or more, and moreover develop appropriate conversation, presumably different for each. I mean, she had a bit of conversation with me. I forget exactly what it was, but it did refer to the achievement for which I'd been awarded.
Okay, so she kind of introduced
you. Yeah. No, I'm sure she had a prompt, probably. Yeah, but to have to do that for an hour's worth of people is not entirely trivial for someone in their 80s. So I thought she handled it really quite well.
Fantastic. And what was she like to kind of interact in your interactions with her?
Well, it was very brief. We basically had about 30 seconds of conversation in total. But she was pleasant. Yeah.
Well, thank you so much for your time. Really appreciate it.
Okay.
And thanks for listening, and stay connected. For further readings and resources about the topics covered in today's episode, check out the links in the description. Thanks for listening, and stay connected.